In our last video, we talked about basic data types in Go, and we talked particularly about integer and float data types. Now, it turns out that there are infinitely many numbers, and our computers aren't infinitely big. So we make some trade-offs and compromises in terms of how we actually represent numbers in computers. And we see this in Go in the integer types, where there are actually 4 different basic integer types. When we say int, our machine will decide whether it's going to do int 32 or int 64, probably based on the underlying architecture. I have a 64-bit laptop, so when I say int on this machine, I end up with an int 64. So an int 8 is going to be an 8-bit number, and so they come in 2 variants. There's int 8 and uint8. U here stands for unsigned, so it can only represent positive numbers. So you'll see that I've declared the variable a to be an assigned 8-bit integer, and its maximum possible value, which I've assigned here, is 127. The unsigned int ranges from 0 to 255. I've assigned that to 255. An interesting thing happens when I add 1 to each of these variables. They're going to overflow. They exceed the capacity of the type. So if I run this program, you'll see that the outputs, A was 127. When we added 1 to it, it became negative 128. We'll talk more about why that happens. The 255 wrapped around to 0. On the 16-bit integers, the positive and negative go from 32,767 to negative 32,768. Interestingly, there's one more negative number than there is positive number. And then the unsigned goes from 0 to 65,535. The 32-bit integers, I'm showing the largest negative value here. And then, so that's when it wraps around, we subtract 1 from that, we end up with 0. Actually, no, we end up with the largest possible positive value. And then another interesting thing that I want to point out here is because there's one more negative number than there is positive number, sort of the intuitive way to define an absolute value function, and interestingly in Go there's not a built-in one for integers, would be this. We would say if x is negative, we return the negative of x, otherwise we return x. This works for every number except the largest possible negative number. So if I take the absolute value of I, which is a negative number, I get back that same number. If I take the absolute value of that number plus 1, so it's a slightly smaller, large negative number, then that actually works. So that's an interesting thing to keep in mind. There is one more negative number than positive number. And you have to be very careful if you make an assumption about the absolute value, because it doesn't work in every single case. Then for 64-bit numbers, the range gets much, much larger, as you might expect, having more bits. Now, I've shown another interesting thing here to think about with integers, where we have to worry about what happens when we do this math. Right? So we've talked about how when we add 1 to these numbers, they wrap around and they become either 0 for the unsigned case or a really large negative number for the signed case. So you might want to try to prevent this thing from happening. You might ask yourself, okay, well, gee, what if happens if I'm going to add 5 to m? Is that going to get greater than the maximum possible integer? We get that maximum possible integer from our constants here. And so you'll see that they're all defined. This is actually how you define constants in Go. We haven't talked about that before. You say const. The parentheses are for when you're listing a collection of them. You don't need them if you have only one. And then you would say a name and then a value. Go uses capitalization to determine if something is public or private. So all the constants that should be used outside of this file, this package, are going to be capitalized. Int size is used only in the definition of other constants, and is in lowercase, it's private. And so we can see that the max int for 64-bit is we take -1 and we shift it left 63 bits. Okay, so going back to our code, if we're trying to add 5 to m and we're asking, is that going to overflow? Is that going to be bigger than the max? The trouble is that when it's done this math, it's already overflowed before it gets to the comparison. So this m plus 5 can never be bigger than that value. And so it's giving us a hint here. It says no value of the type is greater than math in 64. So it has to evaluate this before it does the comparison. That will never actually detect the potential overflow. So if you want to detect a potential overflow, you need to do something like this, where I subtract 5 from the largest possible integer, and I ask, will m be bigger than that? And so you'll see here, when I run this, m, when I try to add 5 to it, and I do the test this way, I don't see the message overflow detected. But when I do it this way, I do get the message that I'm looking for, that the overflow will happen if I add 5 to m. Okay, so let's talk a bit more about why this interesting wraparound happens. This would be a 4-bit 2's complement. I got this picture from Wikipedia. So with 4-bit numbers, they range from 0000, adding 1 all the way around to 1111. For the unsigned, we see what we would expect. So 0 through 15 are the positive values. If you add 1 to this, you could imagine get a 0, carry the 1, get a 0, carry the 1, get a 0, carry the 1, get a 0, carry the 1. This 1 would just sort of fall off. So adding 1 to this gives me back 0. So that's when we add 1 to the largest unsigned value, we get 0. Now, how we represent negative numbers is a decision. And there's a couple things you could do. One of which is you could just say, like, I'm going to make this beginning bit be the sign. It's not represented in this diagram. You could just make this be a sign bit and then have the remainder of the bits be the value of the number. There's 1's complement where you flip all the bits if we have a negative number. So this 0 to make -0, we flip all the bits, we get 1111. This 1's complement and the sign bit notation both have the interesting detail that there would be 2 different versions of 0, positive 0 and negative 0. There's lots of issues with doing either 1's complement or the sign bit, is that you have to have a lot more conditions whenever you do anything. Like if I want to add numbers, we have to think about, okay, are they the same sign? If they're the same sign, then I can add them and keep the sign. If they're different signs, I have to think about which number is bigger. With 2's complement, really all the math just works beautifully, and that's why computers implement this. So what we actually do is we represent -1 by representing -1 plus 16, or plus 2 to the number of bits. So like for a 32-bit number, -1 would be -1 plus 2 to the 32. Then when you add 1 to -1, you don't actually have to think about the sign at all. The right thing just happens. So subtracting would go counterclockwise around this ring. Addition would go clockwise around this ring. Everything works except at this one point of discontinuity. And so we've highlighted that one point of discontinuity in our code. When we go from the largest possible value and we add 1, we loop around to the largest negative value. So that's how 2's complement works. It has this nice feature that is, if you don't have any overflow, you can just do math without thinking about the sign, and the right thing happens. And that makes our hardware simpler and our software simpler. And so that's what was selected. Right, when we think about floating point numbers, the reason they're called floating point numbers is the amount of precision changes. And so it's not like you have a decimal point with like 2 digits of precision after it. You have different amounts of precision. And so floating point numbers are actually stored in exponential notation. So we'll go over here. We're used to exponential notation. I probably first saw that in chemistry class with Avogadro's number, like 6.022 times 10 to the 23rd. So this number here is represented in the exponential notation. This is 3.402 ... times 10 to the 38th power, which is about the largest value that a float 32 can take on. We can see that here in our constants. Here is actually the largest value. So you'll see there's a lot more digits of precision there. And then we have our smallest value. Both of these are in exponential notation. Our exponential notation is in binary, though, not decimal. So here for floating point numbers, we do have a sign bit. We then have an exponent, a section 11 bits reserved for the exponent in the 64-bit float, and then 52 bits of fraction. And so our number is represented by -1 to the sign, so it's either positive or negative. We implicitly have a 1 point and then our 52 bits. And then there's, instead of times 10 to the whatever, it's times 2 to the exponent. And then they subtract 1023 so that we have both positive and negative values here represented with a positive number. We don't need a sign bit in the exponent. And so with that, what we get is a lot more precision where we're near 0. So where we're near 0, so like 10 to the -12th, we can actually get about 10 to the -28 of precision with a 64-bit float, and a little closer to around 10 to the 19 with a 32-bit float. As our numbers get bigger, we have less precision because we have more precision we're using to the left of the decimal point, so we have less precision to the right of the decimal point. So we'll highlight that in this float sizes program. So here I'm going to take these largest numbers. If I add 0.01 to them, they aren't going to change. So you'll see that I print out A and C, and then I print out, I should say B. So I print out A and B. And they are equal, even though I've added 0.01, because there wasn't enough precision to capture adding 1/100th to this really large number. So same thing with C and D. When we add 0.01 to this really large float number, we don't get a difference. We can see the difference highlighted a bit more here in this example. We're going to take the number 1 million. So 1 million, when we add 0.01 to that with a 32-bit float, it doesn't actually change. So here we're printing out with 2 decimal points after the value. So E and F. E and F end up being the same value. G and H are equal also. Actually, G and H are not equal because when we have a float 64, we have enough precision to get that 1/100th. So we look back at our diagram here. So we're around 10 to the 6th. So at 10 to the 6th, we're just missing enough accuracy to do a 0.01 change, but we have plenty of accuracy with 64 bits. So the way to think about this is to realize that we have more digits of precision after the decimal point for numbers that are near 0, and fewer digits of precision after the decimal point, and even before the decimal point for numbers that are far away from 0. So if we go back to that diagram, you'll see that when we get out to around 10 to the 12th, we're no longer able to see precision in 32-bit to around 10 to the 5th. So we're going to be jumping by order 100,000 every time we can do it a small increment of change when we're out to around 10 to the 12th. So when you're using floating point numbers, you need to keep in mind that you may not be able to represent numbers as precisely as you expect if you are further away from 0.